In atomic physics and spectroscopy, exchange-Slater integrals play a crucial role in calculating the energy of electronic configurations. These integrals are essential for ensuring the conservation of angular momentum in the Coulomb electrostatic operator. The authors of this paper investigate the variations of exchange-Slater integrals with respect to their order, focusing on inequalities that govern their behavior. The Coulomb electrostatic operator is formulated mathematically, revealing the significance of exchange integrals in maintaining angular momentum conservation. The Racah inequalities, a fundamental concept in this context, are generalized to derive further relations. The authors present two novel inequalities involving 3 and 4 exchange integrals, which can be exploited to uncover regularities in complex atomic spectra and classify energy levels. These inequalities offer a powerful tool for deciphering the intricate patterns underlying atomic spectra, enabling researchers to better understand the energy level structure of atoms. The results have far-reaching implications for the development of more accurate computational models and the interpretation of spectroscopic data. In atomic physics, the evaluation of electron-electron matrix elements is crucial for understanding various atomic spectra properties. The direct contribution to these matrix elements is expressed as an infinite sum of terms, each involving a radial integral Fk and angular coefficients Ck. The exchange contribution simplifies using the Kronecker delta function and involves another radial integral Gk. These angular coefficients, known as Gantt coefficients, are essential in evaluating multiple integrals involving spherical harmonics, which are commonly encountered in atomic physics problems. The radial integrals Fk and Gk, referred to as Slater integrals, can be evaluated analytically for a Coulomb potential. To avoid fractional coefficients, Condon and Shortley introduced a modified definition of Fk and Gk. The exchange-Slater integrals, particularly G1, play a crucial role in understanding specific properties of atomic spectra, such as the concentration of oscillator strength towards the high-energy side of the transition array. This property is connected to the concept of emissive zones, and is responsible for the asymmetrical shape of transition arrays. In atomic physics, the exchange interaction energy is significant in determining the energy level spectrum, particularly in configurations with two open subshells having the same principal quantum number. The upper and lower groups of levels have different relative contributions to electronic transitions, leading to intense lines in radiative or Auger spectra originating from the upper group of levels. This refined version maintains the technical accuracy and depth of the original content while condensing it into a concise form suitable for voiceover narration. The strength of electric dipole lines linking an alpha-J level of configuration ln plus 1 to the configuration lane plus 1 ln is given by equation 9, involving the coefficient of the G1 Slater integral in the energy of the alpha-J level, C, G1, alpha-J, and the radial integral I, NL, defined in equation 10. The J-file sum rule for electric quadrupole lines is given by equation 11, involving the coefficient C, G2, alpha-J, and the radial integral J, NL, defined in equation 12. The reduced matrix element, ang bracket left L, C, 2, L, ang bracket right 2 is evaluated in equations 13 and 14 for specific values of L and L. The G1 Slater integrals play a crucial role in characterizing the singlet-triplet mixing in configuration interaction studies. The inequalities in equations 15 and 16 are derived from the positivity of the integrand of the right-hand side of equation 5, and Racah's proof of the positivity of Gk. Cowan's observation in equation 17 is mentioned, stating that exchange integrals usually satisfy a specific ordering. The present work builds upon Racah's integral approach to derive new identities for exchange-Slater integrals. Two inequalities involving 3 and 4 consecutive exchange-Slater integrals are derived, which can be useful in detecting regularities in complex atomic spectra and classifying energy levels. These relations can provide insight into the relative importance of contributions to the energy of a configuration and the relative importance of emissive zones. Sugar's work applied Racah tensor operator methods to evaluate the angular part of energy matrices for 4D4F transitions in rare earth ions. By adopting Fano, Pratt's, and Goldschmidt's approach, the recoupling process was simplified to one coefficient, which was then calculated using Utsis et al.'s diagrammatic methods. The resulting energy levels and relative oscillator strengths showed good agreement with experimental absorption spectra. The paper further investigates how energy levels change when certain exchange-Slater integrals dominate, particularly in the vicinity of particle-hole coupling, where only exchange-Slater integrals are non-zero. For configurations with one vacancy, energy levels can be classified to preserve parentage by diagonalizing the matrix of the coefficient of the main Coulomb exchange integral G1. New inequalities are presented, which cannot be derived from existing ones. These novel relations, along with the technique used to obtain them, are discussed in detail. Possible extensions to the relativistic case are also considered. The section concludes with a recall of Racah's inequalities and a case study involving one exchange-Slater integral GK, demonstrating the applicability of these methods to specific problems. These advances in Racah tensor operator methods have significant implications for the calculation of energy levels and oscillator strengths in rare earth ions, enabling more accurate modeling of 4D4F transitions. The research focuses on the case of two exchange-Slater integrals GK, which are crucial in understanding the behavior of certain quantum systems. To derive an inequality involving these integrals, the authors introduce a new function psi k, x, as a linear combination of phi k, x, and phi k plus 1, x, where phi k, x, is a Slater-type orbital. The function f, x, is then defined using psi k, x, and its derivatives are calculated to obtain an expression for the second derivative of x caret k plus 2 psi k, x. The authors use integration by parts to simplify the expression for gk, 2k plus 1 gk plus 1 half k plus 3, which involves the second derivative of x caret k plus 2 psi k, x. This process leads to the inequality gk, 2k plus 1 gk plus 1 half k plus 3 is greater than or equal to 0, which is identical to equation 110 in a referenced work. This result is significant because it provides a new perspective on the relationship between exchange-Slater integrals, shedding light on the underlying physics of quantum systems. In the context of three exchange-Slater integrals GK, a novel function chi k, x, is introduced, defined as a combination of phi k, x, phi k plus 1, x, and phi k plus 2, x, with specific coefficients. This leads to the definition of another function f, x, expressed in terms of chi k, x, and its derivatives. The first and second derivatives of xk plus 3 psi, x, are then derived, involving integrals of yk and yk plus 1f, y, over different intervals, as well as terms involving x raised to various powers and f, x. These expressions highlight the interplay between the introduced functions and their derivatives, showcasing the intricate relationships within the system. The authors derive a recursive relation for the exchange-Slater integrals GK, starting from equation 36, through a triple integration by parts, resulting in equation 37. This relation implies the inequality 38, demonstrating that GK, 2k plus 1, 2k plus 2, 2gk plus 1, 2k plus 2, 2k plus 4, plus gk plus 2, 2k plus 4, 2k plus 5, is greater than or equal to 0. This relation cannot be deduced from previously published inequalities. The authors introduce a new function a to k, x, in equation 39, for deriving a similar recursive relation for four exchange-Slater integrals gk. This function is defined in terms of phi k, x, with coefficients involving binomial coefficients and factorials. The recursive relation has significant implications for the calculation of exchange-Slater integrals, crucial in quantum mechanics and atomic physics, offering a novel and efficient method for computing these integrals. The paper introduces a novel method for deriving closed-form expressions for Slater integrals, a fundamental concept in quantum mechanics. It begins by establishing the relationship between generating functions and Slater integrals. The authors then provide a detailed derivation of the formula for one Slater integral, followed by the case of two integrals, and extend this method to 3 and 4 integrals. For the three-integral case, the authors employ a generating function that involves a linear combination of phi k, x, phi k plus 1, x, and phi k plus 2, x. Applying the same procedure as before, they obtain an equation for chi k, x, and solve a system of equations to find the coefficients in front of the GK Slater integrals. This process is repeated for the four-integral case, leading to the second main result of the work. Although a generalization for an arbitrary number of exchange Slater integrals could not be found, the method can be applied to higher numbers of integrals using computer algebra systems like Mathematica. The most challenging part is finding the coefficients in front of the GK Slater integrals, which requires solving a system of equations. The system of equations derived from the four-integral case of the research is presented in this section. It consists of four independent equations, which, when solved, yield the coefficients for the functions phi k, x. The system is redundant and can be simplified to a set of four equations, where each equation represents a constraint on the coefficients alpha k, beta k, gamma k, and delta k. The solution to this system yields the coefficients as a function of k, which are then used to calculate the functions phi k, x. This process is crucial for the development of the theory presented in the paper. In the realm of spectroscopic problems, the authors delve into the discussion of relativistic effects, particularly focusing on the derivation of non-relativistic radial integrals from Breit-Dirac equations in a relativistic central field or Hartree-Fock calculation. They draw upon Larkin's work, which proposed expansions of non-relativistic Fk and Gk Slater integrals in terms of their relativistic counterparts. However, Larkin's method was limited to average energies, prompting Bauchi et al. To propose new expansions for Fk integrals using the equivalent operator formalism. The authors emphasize the significance of the linear approximation, which is well suited for moderately ionized atoms, where spin-orbit interaction dominates over other magnetic interactions. They provide equations 54 and 55, which express non-relativistic exchange Slater integrals GKNR in terms of relativistic ones GKR, utilizing statistical weights Wjj. Moreover, they discuss the importance of considering the Breit interaction, which cannot be neglected, even for moderately ionized atoms. They reference Ref. 31, which defined spin-orbit integrals by averaging two-particle relativistic operators over all states of a given configuration. The authors also stress the necessity of using relativistic wave functions, not only at high values of effective nuclear charge but also for the outer shells of heavy atoms due to the shrinking of inner shells. Janáuskas and Karaszége's work is referenced, which obtained relativistic analogues for integrals of Coulomb, spin contact, spin-orbit, and spin-spin interactions using the equivalent relativistic operator. Finally, the authors present equation 56, which gives the solutions in spherical polar coordinates, and equation 57, which defines the radial Slater integrals Fk and Gk in terms of the large and small components p and q. Atomic spectra and radiative transitions are crucial in understanding various astrophysical and fusion plasma phenomena. Exchange Slater integrals play a vital role in this context, and developing new inequalities for these integrals can significantly enhance our understanding of atomic structure and spectra. This paper generalizes the technique used by Racah to derive new inequalities involving 3 and 4 exchange integrals, providing a powerful tool for checking the validity of advanced computations and shedding light on interesting features of atomic spectra, such as propensity rules. The authors begin by highlighting the importance of atomic spectra and radiative transitions, citing seminal works by Sobelman and Cowan. They then provide a historical context for Slater integrals, introduced by Slater in 1929, and their role in atomic structure and spectra. The paper also references key contributions by Gaunt, Yulin Shu, Nakvi, Ruano et al., and Hay, showcasing the significance of screened hydrogenic wave functions, relativistic screened hydrogenic radial integrals, and Coulomb approximation in spectroscopy. The main contribution of this paper lies in the derivation of new inequalities for exchange Slater integrals. The authors generalize Racah's technique to derive two novel inequalities, involving 3 and 4 exchange integrals, respectively. These inequalities have the potential to validate advanced computations and provide insights into atomic spectra features, such as propensity rules. The paper concludes by discussing the potential applications of these new inequalities and outlining future work directions. The authors plan to extend this work to derive similar inequalities for relativistic Slater integrals and to tackle the general Racah integrals. This research has significant implications for advancing our understanding of atomic spectra and radiative transitions, with potential applications in astrophysical and fusion plasma research. The theoretical framework for understanding atomic properties in hot plasmas, with a focus on the interaction between atomic configurations and their spectral characteristics, is discussed in this section of the research paper. Key studies contributing to our understanding of these interactions are cited, including works by Bauchi et al., Curtis, Payne, and others. The specifics of atomic structure and spectra are explored, referencing seminal works such as those by Racah, Fano, and Jussies. The importance of mathematical tools like the Jussies-Levinson-Vannes method and the use of graphical techniques for summing and integrating spherical harmonics, as developed by Massot et al., is discussed. Relativistic effects in atomic fine structure are also examined, with references to studies by Armstrong Jr. and Larkins. The relationship between non-relativistic and relativistic calculation schemes is explored, citing Jaunauskis and Karaziej's work on general relations between radial integrals. The paper concludes with a discussion on the use of computational tools, specifically Mathematica, for analyzing atomic properties. The significance of understanding the complex interactions between atomic configurations and their spectral characteristics is emphasized, as well as the importance of utilizing advanced mathematical and computational techniques to accurately model these phenomena. The authors cite two key challenges in existing approaches to federated learning: heterogeneity and non-independent and identically distributed, non-IID, data. Heterogeneity refers to the varying computational resources and capabilities of client devices, which can lead to straggler effects and slow down the learning process. Non-IID data, on the other hand, arises from the diverse user behaviors, preferences, and environments across clients, resulting in biased and inaccurate models. To address these challenges, the authors propose a novel federated learning framework that incorporates a hierarchical clustering algorithm to group clients with similar data distributions. This approach enables more effective knowledge sharing and aggregation among clients, reducing the impact of non-IID data. Furthermore, the authors introduce a dynamic resource allocation strategy that adapts to the heterogeneous computing resources of clients, mitigating straggler effects and improving the overall efficiency of the learning process. The authors evaluate their proposed framework through extensive experiments on real-world datasets, demonstrating significant improvements in model accuracy and convergence speed compared to existing federated learning approaches. Specifically, their results show that the hierarchical clustering algorithm reduces the negative impact of non-IID data by up to 30%. While the dynamic resource allocation strategy improves the learning speed by up to 40%. The authors also discuss the limitations of their approach, including the assumption of a fixed number of clusters and the potential vulnerability to adversarial attacks. They suggest that future work should focus on developing more robust and adaptive clustering algorithms, as well as exploring the application of their framework to other distributed learning scenarios.